So let us define first what is a regression analysis. Regression analysis is a set of statistical methods used for the estimation of relationships between a dependent variable and one or more independent variables. It can be utilized to assess the strength of the relationship between variables and for modeling the future relationship between them. Regression analysis produces a regression equation where the coefficients represent the relationship between each independent variable and the dependent variable. So let me give you an example of application for regression analysis. So whenever we want to know the relationship between level of education and income, between the price of a house and the square footage, between the sales volume for a company relative to the dollars spent on advertising, we use regression analysis. Also, when businesses are trying to decide which location is best for a new store or branch office, regression models are often used. So in other words, the applicability of regression analysis is virtually limitless. So the purposes of regression analysis are basically to: number one, understand the relationship between variables, and to predict the value of one variable based on the value of the other variable. So there are two types of variables in regression analysis. We have the dependent variable or the response variable. This is the variable whose values we want to explain or predict. Its values depend on something else, and it is usually denoted by y. The other one is the independent variable, or the explanatory or predictor variable. This is the variable that explains the dependent variable. Its values are independent as the name implies, and it is usually denoted by x. So in a typical graph, dependent variables are represented by the y-axis or the vertical axis, while the independent variable is represented by the x-axis or the horizontal axis. There are three types of regression analysis. We have the linear regression, the multiple linear regression, and the nonlinear regression. However, in this discussion, we will only deal with the simple linear regression. Now, what is a scatter diagram? A scatter diagram or a scatter plot is a graph of data or mathematical diagram using Cartesian coordinates to display the values for typically two variables for a set of data. So this diagram is used to find the correlation between these two variables, the independent and the dependent variables, and how they are related. After determining the correlation, you can then predict the behavior of the dependent variable based on the measure of the independent variable. So all throughout the discussion of regression analysis, we will use the example of AAA Construction Company. AAA Construction Company renovates old homes in Albany. Over time, the company has found that its dollar volume of renovation work is dependent on the Albany area payroll. So the figures for AAA's revenues and the amount of money earned by wage earners in Albany for the past 6 years are presented below. Economists have predicted the local area payroll to be $600 million next year, and AAA wants to plan accordingly. So in this particular case, we wanted to know the relationship between AAA's sales in relation to the Albany's area payroll. So now we can identify that our independent variable is the local payroll, while our dependent variable is the AAA's sales. So based on the given data on area payroll and sales, we are now going to plot it in a graph. And this is what the scatter diagram would look like. So as you can see, payroll, which is our independent variable, is plotted on the x-axis, while sales, which is our dependent variable, is plotted on the y-axis. So this graph indicates that higher values for the local payroll seems to result in higher sales for the company. There seems to be no perfect relationship because not all points lie on a straight line. But still, there is a relationship. A line has been drawn through the data to help show the relationship that exists between the payroll and sales. The points do not lie on the same line, so there would be some errors involved if we tried to predict sales based on payroll using this or any other line. A scatter diagram cannot give us the true relationship between payroll and sales, but by drawing a straight line, it helps us show the relationship between the variables. In fact, many lines could be drawn through these points, but the question is, which one best represents the true relationship? Regression analysis provides the answer to the question.
Simple linear regression. In any regression model, there is an implicit assumption which can be tested that a relationship exists between the variables. However, there is also some random error that cannot be predicted. The underlying simple linear regression model is y is equals to b0 plus b1 times x plus e, where y is a dependent variable or response variable, while x is an independent variable or predictor variable or explanatory variable, while b0 is the intercept or the value of y when x is 0, while b1 is the slope of regression line, and e is a random error. The true values for the intercept and slope are not known, and therefore, they are estimated using sample data. The regression equation based on sample data is given as y is equals to b0 plus b1 times x, where y is a predicted value of y, b0 is the estimate of b0 based on sample results, and b1 is the estimate of b1 based on sample results. So basically, it's the same as a simple linear regression model, except that this is based on samples and the random error has not been added. In the AAA construction example, we are trying to predict the sales. So, the dependent variable or the y would be sales, while the variable that we use to help predict sales is the local payroll. So, the independent variable or the x would be the local payroll. Based on the given data, here is the graph. From this, we can draw any number of lines. Although any number of lines can be drawn through these points to show a relationship between x and y, the line that will be chosen is the one that in some way minimizes the error. Error is defined as actual value minus predicted value. Errors may be positive or negative. The average error could be 0 even though there are extremely large errors, both positive and negative. So, to eliminate the difficulty of negative errors, cancelling positive errors, the errors can be squared. The best regression line will be defined as the one with the minimum sum of the squared errors. In order to get the equation of the best regression line, or the line that would minimize the sum of the squared errors, statisticians developed the simple linear regression equation y is equal to b0 plus b1 times x, in which the following formulas can be used. Average of x values is equals to summation of x over n, while the average of y values is equals to summation of y over n, and the b1 is equals to the summation of x minus average of x values times y minus average of y values over the summation of x minus average of x values squared, and the b0 is equals to the average of y values minus b1 times the average of x values. So in the AAA construction example, we can get the average of x values as equal to 4, while the average of y values is equal to 7, while the b1 is equal to 1.25 and the b0 is equal to 2. So the estimated regression equation would be y is equal to 2 plus 1.25x, or sales is equal to 2 plus 1.25 times the payroll. So if the payroll next year is 600 million, which means x is equal to 6, since the payroll is in 100 millions. So the projected value would be y, or the sales, is equal to 2 plus 1.25 times 6, which is equal to 9.5, or $950,000, since the sales is in $100,000. One of the purposes of regression is to understand the relationship among variables. This model tells us that for each 100 million increase in the payroll, we would expect the sales to increase by 125,000, since B1 is equal to 1.25 times 100,000, or 125,000. This model helps AAA construction see how the local economy and company sales are related.
Before I discuss how to measure the fit of regression model, let's tackle first why we need to measure the fitness of regression model. Questions usually raised after creating regression models are the following. How do we know that the model is actually helpful in predicting y based on x? Or in our case, the AAA construction, how helpful is the model in predicting the sales based on the payroll? Should we have confidence in this model? Does the model provide better predictions, smaller errors, than simply using the average of the y values? So how do we measure the fit of the regression model? First, we will use the sum the squares total to measure the total variability in actual sales about the average mean of the sales. So the formula is the sum of squares total equals sum of actual sales minus the average mean of sales squared. However, a regression line may be used to predict the value of sales. And while there are still errors involved, the sum of these squared errors will be less than the total sum of squares. The sum of squared errors is equals to sum of actual sales minus the predicted value of sales squared. Showing to you the table 4.3 sum of squares for AAA construction. As you can see, we have here the average mean of actual sales, which equals to 7, the sum of squared totals, which equals to 22.5, and the sum of squared errors, which equals to 6.875. Table 4.3 provides the calculations for the AAA construction example. The average mean of actual sales, which equals to 7, is compared to each actual value of sales, and we get the SST of 22.5. The predicted value of sales for each observation is computed and compared to the actual value of sales. This results in SST of 6.875. As previously computed, the sum of squared errors is much lower than the sum of squares total. Using the regression line has reduced the variability in the sum of squares by
22.5 minus 6.875 is equal to 15.625. This is called the sum of squares due to regression and indicates how much of the total variability in sales is explained by the regression model. Mathematically, this can be calculated as sum of squares due to regression equals sum of predicted value of sales minus the average mean of sales squared. Figure 4.2 displays the data for AAA construction. The regression line is shown, which is predicted value of sales equals 2 plus 1.25x, as is a line representing the average mean of sales, which equals to 7. The errors used in computing the sums of squares are shown on this graph. Notice how the sample points are closer to the regression line than they are to the mean.
Now let's proceed to the coefficient of determination. The coefficient of determination is the proportion of the variability in y that is explained by the regression equation. It is denoted by r squared. The formula for coefficient of determination is r squared is equals to SSR over SST, or 1 minus SSE over SST. Thus, r squared can be found using either the SSR or the SSE. The SSR is sometimes called the explained variability in y, while the SSE is the unexplained variability in y. For the given example, for AAA construction, we already have the SSR, which is equals to 15.625, and SST, which is equals to 22.5. Now, to solve for the coefficient of determination, we have r squared is equals to 15.625 over 22.5. So the answer is 0.6944. This means that about 69% of the variability in sales, or y, is explained by the regression equation based on payroll, which is the x. If every point in the sample were on the regression line, meaning all errors are 0, then 100% of the variability in y can be explained by the regression equation. So r squared is equals to 1 and SSE equals to 0. The lowest possible value of r squared, or the coefficient of determination, is 0, indicating that x explains 0% of the variability in y. Thus, r squared, or the coefficient of determination, can range from a low of 0 to a high of 1. In developing regression equations, a good model will have an r squared value close to positive 1. Another measure related to the coefficient of determination is the coefficient of correlation. This measure also expresses the degree or strength of the linear relationship. It is usually expressed as r and can be any number between and including positive 1 and negative 1. As we can see, the value of r is the square root of r squared, or the coefficient of determination. Please note that it is negative if the slope is negative and it is positive if the slope is positive. The given example for AAA construction, we have r squared is equals to 0.6944. So, to solve for r, we have the square root of 0.6944, or the answer is 0.8333. The answer is positive because the slope is positive 1.25. In this figure, we illustrate the 4 possible scatter diagrams for different values of r. In figure A, we have the perfect positive correlation. When r is equals to positive 1, it indicates a perfect positive linear relationship. As one variable increases in its values, the other variable also increases in its value through an exact linear rule. As we can see, In figure A, the line goes upward from left to right. In figure B, we have positive correlation when r is greater than 0 and less than 1. And in figure C, we have no correlation when r is equals to 0. It indicates no linear relationship. So we see here the dots are scattered away from the line. And in figure D, we have the perfect negative correlation when r is negative 1. It indicates a perfect negative linear relationship. As one variable increases in its values, the other variable decreases in its values through an exact linear rule. So as we can see in figure D, the line goes downward from left to right. Using computer software for regression. The following are the steps on how to use the computer for regression. To proceed, we will have to go on each of the following steps. Accessing the regression option in Excel. First, in accessing the regression option in Excel, go to the Data tab and select Data Analysis. If Data Analysis does not appear, then you have to enable or activate in the Excel add-in the Data Analysis from the Analysis toolpack. Once it is activated, it will remain on the Data tab for future use. When the Data Analysis window opens, scroll down and highlight Regression and click OK. After clicking the OK button, the regression window will open as shown in this sample. You can now input the X and Y ranges by highlighting the specific cells. For the AAA construction company example, what is highlighted in the Y range is the values under the sales beginning from 6 to 9.5, and in the X range is the values in the payroll beginning from 3 to 5. Next is to check the labels box because the cells with the variable name were included in the first row of the X and Y ranges. To have the input presented on this page rather than in a new worksheet, select the output range and give a cell address for the start of the output. So in this example, we put in the cell address in the same worksheet. And the next is to click the OK button. After clicking the OK button, the following summary output will be shown in our Excel worksheet. As we have already computed in our AAA construction example, we have here under the coefficients in the bottom, the intercept which is equals to 2 and the slope which is equals to 1.25. And the sum of squares is shown in the column headed by SS. So another name for error is residual. So in this Excel, the sum of squares error is shown as the sum of squares residual. So the values in this output are the same values that we already have computed. The sum of squares regression or SSR is shown to be 15.625. The sum of squares error or residual is 6.875, and the sum of squares total or SST is 22.5. So that values are shown under the SS column. Another one is the coefficient of determination or R squared. It is shown to be 0.6944. So we have here under the regression statistics, and the coefficient of correlation or R is called the multiple R. In this Excel worksheet, we have 0.8333. So this is how to use the Excel in computing for regression. Thank you.